Alright, we're going to start this with our second clicker question. All of the Galilean moons are fairly small. What should this mean about their geology? So based on what we talked about with the moon and the terrestrial planets, what does being small suggest should be going on with the geology of the Galilean moons? A, they should all have active volcanoes but no tectonics like Mars. B, they should be geologically dead like our moon. Or C, they should have tectonics and volcanism like Venus. Go ahead and think about it and we'll discuss in just a bit. Alright, so if they are small, this means they should have lost a lot of their internal heat, and if they don't have internal heat, then they should be geologically dead. It is the internal heat of a terrestrial or small solid object like moons and asteroids that leads to geological activity. So the answer is B. They should be geologically dead like our moon. Okay, quick note, the internal heat of Jovian planets is what drives their weather systems. I forgot to mention that previously, thought I'd mention it now. Alright, so all of the moons should be geologically dead based on their size. Remember, Europa is smaller than our moon, and Ganymede is just larger than Mercury. Both the moon and Mercury are geologically dead, so that's what we expected. However, we actually see evidence that all of these have some sort of active geology. From images of Io, based off of flybys and even things from the Hubble Space Telescope and so on, we've actually seen that Io is the most volcanically active object in the solar system. So Venus has lots and lots of volcanoes, but Io is more active. It has more eruptions. So the energy that is keeping Io heat, it comes from what we call tidal heating. So it does have a great internal heat, and this is constantly being resupplied. This is one of those strange effects because of the orbital resonance. So remember, Io, Europa, and Ganymede have an orbital resonance. Every time that Ganymede has gone around Jupiter once, Europa has gone around exactly twice, and Io has gone around exactly 4 times. What this does is it means that gravity pulls on them always in the same place in their orbit, which causes their orbits to get pulled and tweaked away from a perfect circle. So Io is actually on a relatively highly elliptical orbit around Jupiter. Well, as this happens, it means that it's going to be speeding up and slowing down, but it's also going to be feeling greater gravity and weaker gravity. As it gets in closer towards Jupiter, the greater gravity causes it to stretch out. Then when it swings out farther away from Jupiter, the gravity allows it to relax. So every orbit it gets stretched and relaxed. And remember, Io is orbiting so fast that it takes just less than 2 days to complete one orbit. So this stretching and relaxing is happening very, very quickly. Okay, so all of this leads to a lot of friction, and from that friction we get a lot of heat, keeping Io geologically active. So each flyby and orbiters actually captured multiple eruptions. So from this one, here is one eruption, and over here is another. Okay, here we have a plume from one, and over there is an eruption from another. Okay, so we've seen lots and lots of eruptions from Io. Now, several of these volcanoes have been active the entire time that we've been studying Io. We've actually seen some die out, turn inactive, and other ones actually form. So Io is very, very volcanically active. As we look at Europa, Europa is actually the smoothest object in the entire solar system. It has no features that are taller or deeper than a few hundred meters. Normally, when we're talking about mountains and so on, we're talking about kilometers, maybe even hundreds of kilometers. That's not the case with Europa. We measure in meters and hundreds of meters. We also see that there are no craters on the surface of Europa. Remember back, what does that tell us? It means that Europa has to be geologically active. It has some way of covering up and destroying old craters. So instead of seeing craters, we actually see this cracked surface. From spectroscopy, we can actually tell that Europa, the surface that we see, is made of almost pure water ice. So it has a very icy surface. Now, because of the purity of the ice that we see, this suggests that it is somehow being renewed. We also see some regions that appear to like lava flows. And so we have this area and then this area surrounding it that kind of looks like lava would have spilled out. However, this is not lava like we think of it, in that it's molten rock. Instead, it is liquid water that has flowed out. And so this constant renewing of the surface by water completely repaves it. Now, the heat to keep liquid water in the interior of Europa is also caused by tidal heating, similar to what we just saw with Io. Now, Europa is farther out, so the tidal heating isn't nearly as strong, but it is strong enough to keep a subsurface liquid water ocean. Now, we see that the ice on the surface of Europa appears to be shifting. We see the same sort of flow, this shifting of ice, in the Arctic, okay, so the North Pole. So again, this suggests that there's likely liquid water underneath this icy surface. And if Europa has liquid water, then it has a potential for life. We'll discuss this more later on when we talk about the possibility of life beyond the Earth. Ganymede, as we look at it, has many, many craters, suggesting that it is not very geologically active, and that its surface is much older than Europa. As we look at Ganymede, we see two different types of terrain. We have a dark-colored region and a light-colored region. The dark-colored terrain has many more craters, suggesting that it is older. The lighter terrain has fewer craters, telling us it is younger. Now, as we look at the newest craters, so these really, really bright spots, those are very, very white, whereas the oldest craters are much darker in color. We believe that this is actually being caused due to chemical reactions from sunlight. As sunlight is hitting the ice, it is causing chemical reactions to turn it darker. In this image, we're looking at the boundary between the darker terrain and the lighter terrain. You can see that the darker terrain has many more craters. The lighter terrain has fewer, again indicating the darker terrain is older. We also see some grooves in the lighter terrain, suggesting that there has been some sort of stresses, some sort of tectonic stress that has caused it to move along. One surprising feature of Ganymede is that it has a magnetic field. The magnetic field of Ganymede is actually twice as strong as what we see for Mercury. This suggests that Ganymede must have all of the things necessary for a magnetic field. So it has to have an electrically conducting liquid that has convection, and that Ganymede is rotating fast enough. Okay, our current hypothesis for the electrically conducting liquid is that it is actually liquid water. Okay, that there is a mantle of liquid water that is then generating the magnetic field for Ganymede. Callisto has a very heavily cratered surface. For a long time, we actually assumed that this meant that Callisto was geologically dead, what we would expect for something of its size. However, as we've studied more about its surface, we've found that it has large craters, but no small craters. So it must have some sort of process to be able to destroy smaller craters, but leaving larger craters alone. How this is happening is actually still a mystery. There's a lot of things we just don't understand about Callisto. Another weird thing about Callisto is that it also has a magnetic field similar to Ganymede, which again suggests that it has an interior of liquid water. However, based off of density measurements and other things that we've done, as we've studied Callisto, it appears that it has not differentiated. Differentiation is this process where the heavy stuff sinks down and the lighter stuff floats out. So, for the Earth, we get the iron core and then the rocky mantle and crust. For Ganymede, we expect there's probably is an iron core and rocky interior, and then a mantle of water, and then the icy surface that we see. we expect that's what we see for Ganymede. Callisto doesn't seem to have done that. Instead of having distinct regions of different materials, it appears, based off of these gravitational and density studies, that Callisto is actually completely mixed all the way throughout, which means there's no one region that should have liquid water and therefore generating a magnetic field. So what is going on with Callista? We have no idea. This is an area that we still need a lot more information. So here we have kind of a view of what we think is going on for the interior of the Galilean moons. So Io really is similar to a terrestrial planet. We have an iron core, a rocky mantle, and a rocky surface. Europa is very similar to a terrestrial planet in that it has a rocky core and a large rocky mantle, but we do expect a region of ice and water. Ganymede has a rocky core and a very small rocky interior with a lot of icy or liquid water mantle, and then the ice surface that we actually see. And then Callisto, from what we can tell, is completely jumbled with rock and ice and metal all throughout the interior, and then it has the surface of ice. But again, we don't exactly know what's going on with Callisto. This is an ongoing question. Now, Jupiter doesn't just have the Galilean moons. Altogether, we've discovered somewhere around 79 moons total, which we can split into 3 different groups. We have the 4 Galilean moons. Those are the 4 big ones that are comparable in size to our moon and Mercury. There are 4 small inner moons. These orbit closer to Jupiter than the Galilean moons do. And there are 71 small outer moons. These orbit around Jupiter beyond the orbit of the Galilean moons. The 4 small inner moons are Metis, Adrastea, Amalthea, and Thebe. And all of them are so small they have weird shapes. Notice that we are comparing them to Long Island, New York, where we're looking at around 100 kilometers in size. Now, all of these orbit above Jupiter's equator and orbit in the same direction as Jupiter is rotating, which means they all have a prograde orbit. In other words, they're going the direction that we expect. The 71 outer moons are all beyond the orbit of Callisto and are again small, meaning they will also have weird shapes. Many of them are highly inclined compared to the equator of Jupiter. What that means is their orbits are highly tilted away from Jupiter's equator. Many of these have a retrograde orbit, meaning that the moons are actually orbiting backwards. Our best guess to how these things got there is actually through orbital capture. If you remember back when we mentioned that we had to explain weird things that happen in the solar system, one of those weird things are moons that orbit backwards. Our best explanation for moons that orbit backwards is that they are captured asteroids.